I just want to show you something super cool. For those who are following my channel, you know that I have this compiler which compiles Jupyter Notebook into Docker container images, installing all the dependencies and the actual notebook into the container, pushes it to the registry, and it creates Kubeflow pipeline components out of it. And also you can use them now from the command line. We have a CLI. I mean, that all you should know, but I have now created an additional compiler target. So it takes the notebook, and what it does, it creates a Kubernetes job definition for you. And you see here I have 100 parallel workers. So each worker in a Kubernetes job is basically a pod. So if I go to this console here, you see here there are 100 parallel jobs running, if they are still running, because they are actually computing something. Yeah, they're still running. Let me, I don't need to zoom in. Those are just 100 pods, no? And the way how I parallelize is basically I'm sharding based on input files. And this is pretty cool because I have, in addition to this Kubernetes job target, which I can compile into now, I've also created a generic grid computing wrapper. And let me actually just walk you through this wrapper. It's pretty cool. So I have here a notebook. That's just an ordinary claimed component. No, as you remember, maybe you just have to define the interface here of the component in the notebook, and then it will automatically create the appropriate KFP YAML for it. No, you see here the interface, the inputs. But in addition, the wrapper, it's something which wraps this component, and those components are ordinary algorithms which read data from local storage and write data to local storage. But this wrapper here is relatively tricky. So what it does actually, it computes micro batches, and the smallest micro batch is obviously one file, and that file is on S3, on Cloud Object Storage, no, on COS. And it grabs one file by one, or one batch by one. In this case, it's batch capable, so you can define batches. And obviously, if it's only one file, then it's at batch size is basically one. And what it does is actually it. Let me walk you through the algorithm. It's relatively straightforward. So first of all, we are locking. We are locking the files directly on the object storage side. That way, we have the workers fully independent of any central coordinator. So speaking in Elon Musk terms, no part is good part. And that way the coordination happens via log files and .processed files. So let me actually show you how that works. Obviously, if you are doing it that way, workers can crash, and then the log files might just become stay there and preventing actually further processing of a specific shard. That's why we are deleting the expired log files, and that here you can configure this timeout as a parameter. And if the file is locked still, so the log is not expired, that means a worker is actually working on that shard. We just continue. Also, if it's already processed, obviously we don't process it again. And if not, what we do, we download only the batch, the mini batch, to the local file system. The local file system in this case, since we are running on Kubernetes as a Kubernetes job, it's the transient file system which you have in the pod. And then we just wrap the other claimed component. So any notebook, any script we can wrap basically. And the script itself, it has no clue that it's running in the Kubernetes context, and it has no clue that it's running in this grid computing pattern. So what it actually thinks is it's just working on a huge pile of data. But a huge pile of data is just a micro batch, okay? So what we do is we process, no, and then we compute the output. The algorithm computes some output. That's also files. That means we can, after that has run successfully, we can remove the input files. And then we upload the results of this process. We upload to COS. And then we remove also the results. and then we just marking this file as processed. Okay, and the cool thing is here, with that algorithm, we can basically start as many workers on the planet as we like. In theory, we can start one worker per shard. So in extreme case, we can start one worker per file, and then it ends up to look like this. So we just have here, in this case, 100 parallel workers on OpenShift. And yeah, it's doing its job, and I'm expecting more or less a 100-fold increase of processing time compared to the single threaded version. Yeah, and without changing your algorithm, you're actually making your algorithm capable of running as a worker in a grid computing pattern. So pretty cool. So I'm providing the code very soon. I just wanted to share this with you. Pretty cool. Take care and have fun, and talk to you soon.